Okay. So, welcome everyone. Welcome to those who just joined us. My name is Sarah Mastroni. I'm a program officer at Ocean Visions, and I'm joined here today by my colleague Ruth Driscoll Lovejoy, who is a program director at Ocean Visions. And we are so delighted to be here. This is in anticipation of the upcoming marine carbon dioxide removal in Canada event that is happening next week. And we are so happy to be sort of joining onto this fantastic forum that's going to happen to give you a little bit of a primer on mCDR to make sure that people feel like they're grounded before going into this wonderful event. So big thanks to Eric and the rest of the team for letting us show up in this way. We're really excited. Ruth is going to be at the event next week in person. So definitely track her down if you want to chit chat and talk more about mCDR or anything else ocean climate related. I will be there in spirit, but happy to answer questions today. So before we jump in, I'm going to give you a little overview. So we're going to start out just explaining a little bit of why we're even talking about marine carbon dioxide removal, or mCDR, as I'll probably call it for the rest of the hour. What that means when we say mCDR. So what are the approaches that we're talking about? A little overview of the science and technology. I'm going to spend just a very brief amount of time going over some of the important governance and policy frameworks that are applicable here. And then I'm really delighted to have Will Burt join us today, and he's going to give you a spotlight on Planetary, which is his startup, and they are a group of folks who are actually doing mCDR in Canada. So that's very exciting. And then we'll save some time for some questions and answers. Please feel free to put questions in the chat. Ruth and Eric and Will are available to either type some responses to you as I'm talking, or we can answer them in real time at the end. Questions for myself, questions for Will, also questions about the mCDR in Canada forum. Those are all fair game. Okay, so we're gonna jump right in. So just quickly, who is Ocean Visions? Why are we here? What are we doing? Ocean Visions is a nonprofit. We work to catalyze innovation, and we work right at this intersection of ocean health and the climate crisis. We work with this big network. You can see their logos represented here. These are folks in the academic space, in the nonprofit space, in policy, in the private sector. And this is a really great group of folks with tons of brain power and resources. And this allows us to really fully explore and advance these responsible climate solutions. We work on this four-part strategy. We call it our four R's. It starts with this overarching idea of reach. And this is an idea that to work on these problems, we're actually going to have to build global capacity, right? These are huge problems that we're looking at when we're talking about ocean and climate issues. So it really, it takes a global community. It also takes a lot of different skill sets. We think about marine decarbonization or reduce. So how can we develop ocean-based pathways to a lower carbon economy? We talk about remove, which is marine carbon dioxide removal. How can the ocean contribute to the uptake of greenhouse gas pollution? And then we also work on repair. So looking at critical marine ecosystems that are on the brink of tipping, like tipping points. So today, obviously, we're diving right into remove. But if you're interested in any of these other areas, feel free to check out our website, and there's a lot of more information about that. Okay, so why are we talking about the ocean when we're talking about climate? So overheating and carbon imbalances in the atmosphere are obviously overheating and causing carbon imbalances in the ocean and vice versa, right? So we're in this cycle that we cannot break. About 90% of the excess warming from greenhouse gas emissions has already ended up in the upper ocean. And the ocean has already absorbed about 26% of all CO2 emissions since about the mid 1700s. So in this way, ocean is doing us a huge favor, right? It's slowing the rate of warming that we would otherwise experience, but this does not come without its consequences. So we have thermal stress happening. So ocean warming is responsible for marine heat waves, about 1/3 of observed sea level rise, and decreased ocean mixing, which is decreasing the ability to supply oxygen into the inner layers of the ocean. The surface ocean is also the engine that powers storms. So more of this thermal energy in the upper ocean is going to lead to more powerful storms, which we've been seeing for years now. And then warmer waters are responsible for decreases in sea ice, increases in melting or the loss rates of ice sheets. And to escape these warmer waters, we're seeing a lot of marine animals that are actually moving away from the equator into the poles. The other part of this is the chemical stress. So not only is the ocean absorbing all this excess heat, but it's also absorbing this excess carbon dioxide, right? The ocean and the atmosphere want to be in equilibrium with each other. So when we're pumping more CO2 into the atmosphere, it means the ocean is taking up more carbon dioxide as well. We have ocean acidification. I'm sure most of us are familiar with this. I won't go into detail, but the acidity has increased about 30%, which is enormous and has huge consequences for marine life and ecosystems. So collectively, we've delayed action for so long on emissions reductions that now we're seeing that carbon dioxide has to be a part of the conversation, right? We have to do the reduction, right? The decarbonization absolutely has to happen, but we also need to be talking about removals. So it must be used to balance the emissions from hard to abate sectors like aviation, right? These areas where we know that reductions are going to happen much more slowly. And then it's really the only tool we have to remove legacy emissions. So the carbon dioxide that's in the atmosphere already, right? We need some way to take that out of the atmosphere. And so the State of CDR report, the second edition, which was released last summer, calls for between 7 and 9 gigatons of CDR per year by 2050 to stay within the goals set out by the Paris Agreement, right? Which is limiting warming between 1.5 and 2 degrees Celsius. Um, and this is huge. I think we kind of can lose track of what we're saying when we talk about gigatons or 7 to 9 gigatons. But this is at the end of the day, a massive quantity of carbon. This is huge. And thus far, we are doing about 2.1 gigatons of CO2 removal per year. And this is mostly coming from what we would call conventional sources. So things like reforestation and afforestation. But in order to actually reach this goal of 7 to 9 gigatons per year, we're going to have to look to other methods or novel CDR. And so that includes things like marine CDR, which we're going to talk about. And a lot of people have heard of terrestrial methods of CDR that include the novel things like direct air capture. And a lot of times people ask us, well, why don't we just do direct air capture? That way, we don't have to mess with the ocean, right? We already have this technology. And I think, in an ideal world, we could just rely on direct air capture. That would be awesome. But the reality right now is that that's actually never going to scale up to where we need to be. And so scientists are looking at the ocean because it's actually the largest reservoir of carbon in our global carbon cycle. So it's really impossible to be thinking about moving such an enormous quantity of carbon from one place to another without thinking about the ocean as one of these places it could go. And the reason for this is that the ocean has two different natural processes by which it moves carbon around. There's a biological process, there's a chemical process. And sort of at the most fundamental level, mCDR is asking the question, can we take these processes that already happen and can we speed them up so that the sort of equalizing of CO2 from the atmosphere into the ocean happens more on a human timescale and not on a geologic timescale? So quickly, I'm going to go through the approaches that are being seen or being explored the most today. I'm going to be just showing graphics instead of putting a bunch of words up on the screen. And these graphics you can all find on our website. I think a lot of us are more visual learners, and sometimes it's just helpful to see things in pictures instead of having a ton of words being thrown at you. So we're going to be looking at biological pathways, which is essentially growing algae in the ocean, whether that's macro or micro. We're going to be looking at adding alkalinity to the ocean, as well as electrochemical methods of carbon removal. So let's start with ocean alkalinity enhancement. And this is the method that Will's going to be talking about with Planetary. So the general idea here is we're taking alkaline materials and adding them to the ocean to enhance its natural ability to take up atmospheric CO2. These minerals can include things like olivine, silicate rocks, limestone, other carbonate minerals. And there are several different ways that people are thinking about doing this. You can spread finely ground alkaline substances in the open ocean, right on the surface. You can deposit alkaline sand or gravel on beaches or coasts. If you're familiar with Project Vesta, that's what they're doing. And then the reacting seawater with alkaline minerals before returning it back to the ocean in more of a closed system. But the main idea is we're adding something alkaline to the ocean. This in turn allows the ocean to actually uptake more CO2 from the atmosphere. And some things to think about when we're thinking about this suite of approaches is this requires some external materials, right? Whatever the carbonate mineral is that you're adding. So where are those coming from and how are we getting those? Oftentimes, this looks like using a lot of potentially using fossil fuels to get those if you're thinking about a bunch of like big equipment. Um, a lot of these techniques, of course, in a perfect scenario, we'd be using renewable energy for all of the energy needs. But of course, that's also a big question, right? There's a lot of demand for renewable energy. So where is that coming from? And then another big question to ask is this process happening in the open ocean, right? If you're spreading it on the surface waters, or in a closed system, like if you're reacting things on land and then returning seawater back to the ocean. And this open versus closed system is actually a very interesting thing to think about because while it's easy to know what we're putting into the system here, whether it's closed or open, right? We know what we're putting into the ocean. It's kind of hard to know what you're getting back or like what is actually happening. And so when things are in a closed system, it's much easier to measure what's going in and what's coming out versus if you're just working in the open ocean. Okay, the next approach is something called electrochemical ocean carbon dioxide removal. And this is where electricity is actually being used to split seawater into its components. So a basic stream and then an acidic stream. The basic stream will be discharged back into the ocean, and then the acidic stream can be neutralized or used in other industrial processes or sequestered geologically. These techniques are also sometimes referred to as direct ocean capture, which draws this comparison to direct air capture. But the main takeaway here is that electricity is actually being used to split seawater. And this happens on land. So here we have the closed system. Um, so easier to monitor what's going in and what's coming out. One thing to think about here, though, is as we're talking about scaling up these technologies, right? If we're ever going to meet those like huge gigaton scale needs that we have, there's often a ton of competition for coastal land and coastal access, right? The coast is always a desirable spot for lots of things, whether that is recreation or fishing or tourism, right? Coast is very expensive. And so could we actually scale this up is a big question there. Okay, this is macroalgae, so growing seaweed. This is essentially intentional additional seaweed growth. So, of course, we have seaweed forests, kelp forests that exist naturally, but the idea here is that we would actually grow more seaweed in the ocean, and then, importantly, you have to do something with that seaweed, right? Because the carbon is being sequestered in the actual living tissue or the biomass of the seaweed. And so then you would need to do something with this biomass to lock the carbon away permanently. So some people are talking about could we sink it to the bottom of the ocean where carbon storage is going to be quite permanent? Could we use that material to use it for some sort of like bioplastic or biomaterial that's going to be around for a long time? These are some of the things that people are talking about with seaweed. And a couple of the sort of challenge points to think about with seaweed growth is in order to, again, reach this meaningful or climate relevant scale, we're not talking about seaweed farms. I think that some of us have in our heads like artisanal seaweed farms or like small scale, right? We're talking about pretty massive operations if we're going to get to the gigaton scale of carbon sequestration. And so then a lot of other interesting questions arise, right? We're creating pretty massive habitat. We know that kelp forests are habitats for a lot of other organisms. So what happens when we create a habitat and then have to essentially take that habitat down, right, to store the seaweed? Seaweed also releases other greenhouse other greenhouse gases. And so, how does that actually stack up against the negative emissions of the CO2 that it's capturing? So, a lot of interesting sort of downstream questions with seaweed. Then we can go on a micro scale with seaweed and think about microalgae or phytoplankton. And this is a really interesting technique where the thought process is that there are limiting nutrients that are basically either saying, yes, that phytoplankton can bloom in the ocean, or no, it can't. And so scientists have asked this question for a while now. Okay, if we just add some of this limiting nutrient, iron is a very common one, can we actually spark a bloom of phytoplankton? That phytoplankton, of course, is composed of microalgae who are comprised of carbon. Can we then take those little guys and either sink them down somewhere or do something with that biomass, right? And so there were actually about 13 experiments conducted on this process in the late 90s, early 2000s. And these experiments sought to just see what is the response of actually adding this limiting nutrient to the water. And it was shown very conclusively that yes, you can add iron to the surface ocean and you can see phytoplankton blooms. That's great. The research now is more about, okay, what happens to that phytoplankton, right? Some of that's going to get eaten. Some of it is going to be remineralized. Some of it will make its way down to the deep ocean where its carbon will be stored on a long scale. But we don't really know what proportion happens or what proportion is going to be in each of those categories. And like everything in the ocean, stuff is very hard to monitor, right? This is a very dynamic and complex system. So trying to track where microscopic organisms go is very, very tricky. Um, yeah, so maybe that's all I'll say about microalgae. MRV, very, very difficult there. Okay, lastly, the last approach that we're going to go over is looking at blue carbon. So historically, the term blue carbon refers to three vascular vegetated ecosystems. Those are mangrove forests, salt marshes, and seagrass beds. More recently, the term blue carbon, some people actually use that to encompass other like photosynthetic organisms or other animals in the water. So that could also include kelp, which is not technically a vascular plant, but it does photosynthesize. Could also include things like marine animals whose bodies contain carbon and they are part of the carbon system. So the global distribution of blue carbon is somewhere between 36 and 185 million hectares, storing as much as 33 billion tons of carbon. And you might be thinking that is a massive range between 36 and 185 million. And it points to one of the big friction points with blue carbon is that we don't necessarily actually have a great sense of how much blue carbon ecosystem we have globally. And so there are large knowledge gaps that remain around the spatial extent of blue carbon ecosystems, as well as their storage capacity. So, like terrestrial plants, the blue carbon ecosystems store carbon. Unlike terrestrial plants, most of the carbon that they're storing is actually not in like their leaves or branches, but actually in their sediments. So it's in like the soils or the ground that their roots are in. And this is really cool because it creates a large capacity for carbon storage. It's very tricky though, because it's very hard to actually get a sense of how much carbon is down there and what the movement is. So you actually have horizontal movement of carbon in these ecosystems, and it's very hard to track. So when we're talking about utilizing blue carbon restoration, right, increasing the amount of these ecosystems or the size of these ecosystems, one of the challenges is that it would actually be very difficult to say with a high degree of certainty how much carbon we are storing. And so there are so many co-benefits to blue carbon ecosystems that we can think about if we're looking at carbon as the main goal or objective, right? There are all these other reasons why blue carbon habitats should be restored and protected. But the argument for using them for carbon sequestration alone is a pretty tricky argument, and you run into a lot of challenges in terms of actually being able to say, yes, we sequestered this much carbon and it's going to stay in this place for this amount of time. And so I want to take a second and actually zoom out a little bit. So we just talked about some of the major approaches to mCDR, the actual science, the technology behind it. But if you take a step back, you see that this is not just a field about science and technology. And I know this is very small. This is like an ecosystem map. And using the term ecosystem in a sort of loose sense here, looking at all of the different fields and sectors that are involved in mCDR, right? So this encompasses philanthropic funders. This encompasses the private sector. This is government. This is registries. This is scientific research institutions and startups and NGOs, right? There are so many different fields that are actually involved in mCDR. And so I want to kind of take a step back and talk about some of the other parts of mCDR that go beyond just the science and the big questions that are still out there. And this takes us to this acronym MRV, which a lot of people throw around. It stands for monitoring, reporting, and verification. And basically, this is just asking where is the carbon, how much has been sequestered, and how durable is the storage. So you can have a project that tries to sequester carbon, but how do you actually know that what you said was going to happen actually happened, right? And so this is really critical for making sure that the carbon is being removed and staying removed. This is very critical if you're using markets to finance this industry, right? We have to have some sort of accountability here. And this is a really key stepping stone for progress in this field at large, right? Without the ability to do MRV, other parts of this puzzle sort of stall out. And so there are bespoke MRV protocols by individual companies, but there's definitely sort of a call for a more standardized protocol for consistency across all of these companies, which is challenging because, as we've just seen, there are a number of different approaches here. And so you can imagine that the equipment, the sensors necessary for the monitoring and verification here are probably going to vary quite a bit between approaches. Just want to spotlight a couple of companies that are working on some of this accountability stuff. So Puro Earth has recently opened up, or they did a public consultation for their latest ocean-based carbon removal methodology, which is around microalgae. Super interesting. And then Isometric also released a direct ocean capture and storage protocol. So just a couple of examples of this accountability piece progressing. Okay, and then I want to just take a few minutes to talk about international governance. So the governance and policy in mCDR is sort of a complicated thing, but is ultimately very important to an important puzzle piece in all of this. So largely, this international law is the body of rules, the principles, the standards that govern the interactions between nation states or sovereign states and the other entities in global relations. And these operate through consent rather than enforcement. So states agree to obey the rules, norms, and standards. Um, and it does not directly impose obligations on private sectors, such as mCDR researchers or companies. Individual actors are required to meet international laws when their country adopts and enforces the contents of the international agreement. And so the existing international legal framework that we have for managing mCDR is really fragmented right now. Um, it's important to note that the agreements that we're going to talk about were not developed with mCDR in mind. So this is sort of a piecemeal approach, right? Trying to sort of see what existing laws are relevant to mCDR. This means there's often really significant uncertainty and complexity around how they apply to mCDR. So the London Convention and Protocol was established to regulate marine pollution caused by ocean dumping, which was defined as any deliberate disposal into the sea of wastes or other matter from vessels, aircrafts, platforms, or man-made structures at sea. And so the relevance here is that activities such as, so like the London Convention parties have determined that ocean fertilization activities fall within the scope of this marine dumping. And that approaches involving the addition of materials to the ocean, such as ocean alkalinity enhancement, where you're adding things like minerals, may also qualify as dumping. Again, these rules were written way before mCDR was a thing that was being discussed. And so the thought was that, okay, anything you're just putting into the ocean is going to be like net harmful to the ocean. Today, of course, we have things being put into the ocean that are trying to help the ocean. So again, this is the sort of like mismatch of terminology. The London Protocol parties have adopted an amendment that's not yet enforced to regulate the placement of matter into the ocean for marine geoengineering activities, which are defined as the deliberate intervention in the marine environment to manipulate natural processes. So as you can see, it's trying to kind of fit around a peg into a square peg here, and there's a lot of interpretation of language and mismatch. But very interesting, the LCLP, and this is something that is very present and ongoing, and I imagine will be discussed next week too. Then we have the UN Convention on the Law of the Sea. This ultimately aims to promote peaceful use of the ocean, equitable, efficient utilization of their resources. How it's relevant to mCDR. The boundaries that are established in here actually determine which country has authority over an mCDR project, right? You can imagine a lot of these projects are happening out, not just on near shore, but out in the open ocean. So requirements for marine scientific research applies to the mCDR field trials. And some of these approaches, again, might be actually viewed as a source of marine pollution and restricted thus under this Convention of the Law of the Sea. The Biodiversity Beyond National Jurisdiction Agreement aims to ensure conservation and sustainable use of marine biological diversity and the areas beyond national jurisdiction. So this is, again, an area-based management tool that could be used when designating areas suitable for mCDR activities or field trials. The Convention on Biological Diversity, which is all about promoting conservation of biological diversity and sustainable use of the components, again, is going to be potentially used for ocean fertilization and geoengineering more broadly. And then lastly, the UN Framework for Convention on Climate Change, or as it's often called, the UNFCCC, is all about achieving stabilization of greenhouse gas concentration in the atmosphere. And so, of course, this also links, or implicitly at least, supports mCDR activities if they prove to be effective sinks. And yeah, I think I'm going to stop there with international governments. I know that's a lot, but these are all, I think, frameworks that are becoming increasingly more important to this field as field trials and open ocean trials are actually starting. And we are understanding more and more how limiting our current framework, current governance frameworks and policies are to this field. Trying to figure out, okay, how do we work with what we have? How do we envision better frameworks for the future? And how do we ensure that this puzzle piece is not the limiting thing that causes everything else to stop in this field? I want to encourage anyone on this call who wants to dive deeper into any of these topics to check out our resources page. This was like a very scratch the surface overview, but if you're interested in learning more about specific field trials that are happening, we have a whole database with that. If you want to go super deep into the science and technology on any of the approaches, we have a series of roadmaps that go very detailed. And if you're curious about who all of these actors are in the space, we have an ecosystem database that provides a pretty comprehensive overview of all the folks in the space right now. If you don't see someone in there that you would like to be in there or should be, you can suggest it too. We are always updating it. And then just a little plug for some of our newest projects that are going to be coming out. If any of these things are interesting to you, keep your eyes peeled. These are coming in 2026. And with that, I'm going to pass the mic over to Will to take this into a more localized context. And Will's going to tell you all about Planetary and what they're doing. So, Will, over to you.
Thanks, Sarah. Hi, folks. My name is Will. I'm an oceanographer, and Sarah referred to Planetary as my company. I wish. I'm the chief scientist of the company, and so I lead all of the MRV work that Sarah was talking about, and all of the ocean safety work, um, and um, and many other things as well. But it's a fun space to be in, and I will try and share my slides as quickly as possible. How's that?
Perfect.
Okay, cool. So, I gave myself a very long title, but I think this is a direct quote that I've stolen from someone named Phil DeLuna. He was describing our project in this way in a recent article that I think is really a great way of thinking about it. In that the project we have in Nova Scotia creates the conditions for learning by doing, because the ocean is a very complex environment, and you can only get so far in the lab. We're doing it in a way that is safe and transparent, and as I'll mention, a scale that really begins to matter. So, as Sarah mentioned, this is ocean alkalinity enhancement, a specific kind that I'll focus on today. And the reason I think it's important to start by saying why, as a scientist, I left my academic position to join Planetary is because I really do believe in this as a concept. The reason is because the problem we face in terms of the climate emergency is a chemistry problem. It's too much carbon dioxide in the air and trying to find an acceptable storage place for that CO2. So it really is a CO2 problem, and this approach focuses on that CO2 specifically. The ecological risks for this type of approach are very well understood, and I'll speak a bit about how we mitigate against those. No solution is without risk. I should be super clear about that, but the risk portfolios for different approaches are very different. And it can reach climate relevant scale, and that's really important too. I don't think, I think it's really important that this type of work be able to get to a scale that impacts the climate, because that's the mission here is to make a climate relevant impact. This is an image created by NOAA in the US back when they had funding. And it sort of just shows that alkalinity enhancement can be very big in terms of its scalability. Conceptually, it can be at the scale that would start to become climate relevant, and that's why it's up here. And it can get very cheap, which means you could actually implement it, at a very big scale and have it make sense from sort of an economic perspective. Those are two really important pieces to keep in mind. So how do we get to the climate relevant scale? Well, we need to do intensive research, and we need to do that research at slow, incrementally increasing scale. And that's what this project kind of has always been. So CO2 in the air and ocean are typically in equilibrium with each other. What we do at Planetary is we add essentially a mineral antacid, so solid minerals that dissolve in seawater. And when they do, they neutralize CO2, which is an acid in seawater, just like stomach acid when you take an antacid tablet. By decreasing the amount of CO2 in the ocean, you can cause CO2 from the air to fill that void. And this is, again, very fundamental chemistry. You can do this in a beaker over and over again and get the same result because it is just chemistry. And the outcome at the end is that you remove CO2 from the air, store it in the ocean, and actually end up deacidifying the ocean just a very small amount. So what does that actually look like in the real world? This is our project site. So this is a drone image of the Nova Scotia power generating facility. So really what's going on here is water is being drawn into the power plant down here. It's coming underneath the plant, going through the turbines. And just before going back into the ocean, we add our mineral here from our site. This is what it looks like when it hits the ocean. It's very bubbly because this ocean outfall is sort of plunging via waterfall. So it doesn't really look any different whether we're adding minerals or not. It just looks like this all the time. So from a different angle, this is what it looks like. This is the site in all of its glory. I call it a tank on a tarp. Really, it's seawater into a tank. You put your mineral in the top, mix it up, and pump it into the outfall that then flows out into the ocean. This is what it looks like from another angle again, and I show all these angles because it's important to understand the footprint of the site. Sarah mentioned earlier, we probably want to be careful about developing technologies that take up large expanses of the coastline. You can see how little space this requires to set up. And so that low footprint is a really important thing to remember. You can also imagine looking at this, how little energy it takes to run this site. It's essentially all measured on a power meter, and it's a very, very small energy requirement. And the cost to set it up is not big either. So these things are important. In terms of creating conditions for learning, this is right in the middle of downtown Halifax. For those of you who are coming to town next week, it's right across the harbor from where you'll be staying, and it's very collaborative. So it brings in the local university, Dalhousie, but also many, many other groups to go out and study this really intensively, and that's important. We're in year three of the project, so we are incrementally scaling. We're at the point now where we're adding this mineral pretty much all the time, except for sort of maintenance windows. And we're at this scale now where we might start to see impacts in that we are not seeing huge changes in chemistry because that's the way the system works, that we're making very small changes to the ocean. But you're not going to start seeing these signals until you scale appropriately. Keeping in mind that we're still more than 100 times away from anything that you'd consider a large scale deployment. We are still very small when it comes to that. But when it comes to understanding the fundamentals and seeing if this is going to work, we are starting to get to that stage where we can answer that question. Okay, so how do we do that? I'm just checking the time here. We have lots of sensors. So we have sensors near the dosing location. We have sensors inside the pipe where the alkalinity is added at different locations. We go out on boats every 2 weeks with researchers, just as a big research team, collect samples in the water, collect samples in the sediments, and combine all this data into quite a large data set. The way that we track and mitigate ocean ecological risks, there's a few different ways. The first way is just tracking the research. So the amount of peer-reviewed literature for ocean alkalinity enhancement has doubled every year for the past 5 years. So just keeping an eye on that is important because there's a lot coming out. We're learning all the time. Probably the most important thing of all is testing the mineral, right? That's pretty logical. The mineral could have impurities in it that change over time. Of course, we know the material very well before any sort of addition happens, but you still have to track that very closely. We do dedicated ecotox studies on different types of organisms. Some are required for regulatory purposes, some are done more for research purposes on local species. We consistently monitor over time. So I think the most important part for a mineral addition like this is the metals content. You don't want to be adding trace metals to the water column in harmful amounts. Of course, minerals have metals in them, so you have some amount, and it's the important part is tracking and keeping a close eye on that. Another really important thing is that you're not pushing the system too hard, right? You don't want to push the pH too high. You don't want to reduce acidity too dramatically because that can be harmful. And so you have sensors reading these measurements all the time. You're making sure your levels are well within sort of acceptable thresholds. Same thing goes for adding particles. You don't want to swamp the water with particles. And there's sensors that can track that. And then finally, we have dedicated research programs. So there's something just now that launched called the Joint Learning Opportunity, where funding becomes available for external researchers to come in, launch new projects, study new uncertainties, and really just throw everything we have at this. So that's why it's such an exciting place. I won't go into the details here, and I'm sorry for how busy this slide is, but the community engagement work here is really, really important. I just want to say that the way we go about this is sort of different levels of engagement that starts with informing, of course, but where we are now is in this sort of collaboration stage, all the way up at here where groups are formally part of this project and start to get to a point where they're empowered within the project. And all of our projects are developed in this way. So it's been some really great progress in that, but it's not my part of the business and I won't elaborate on it here. I think it's really important to be super upfront. This project generates carbon credits. And there's a bunch of reasons why that's important. The first is that we have to prove that this works as an industry, and the moment right now is that carbon credits is how that works. And there's another few really important reasons for that too. So here's how it works. You have all this data that I mentioned. You use that to generate your estimate of carbon removal. So in this case, you've sequestered a bunch of carbon. You can measure certain elements of that. You also have to subtract all the emissions down to the very last detail of how much it required to do that. Then you get a net removal. Okay, so you always have to account for your emissions. Then you tally up all the uncertainties you may have, which in this case, and this is real information, real data, you actually, that could be plus or minus. That's what uncertainties are, right? Plus or minus. Well, we actually subtract those off deliberately. So we're getting the lowest possible estimate we can generate, which means we have the highest amount of confidence that we are undercrediting our work. That then goes through a third-party audit, very intense. I can speak from experience. It goes onto a registry. This isometric registry that Sarah mentioned. This is where the MRV protocol is made. So we follow that protocol. This already exists for this type of carbon removal. And the revenue that generates just goes right back into the project just to keep it going. So we're not at a profitable stage yet. We have dreams to be there, but right now it's about research. It's about learning, and that's what these credits can do. They can keep this project moving. Further from that, you can use these credits to do presentations, do webinars, write reports to regulators, to the public, get feedback about the ways that you've done it. How did you quantify uncertainty? How did you test for ocean safety? Come up with new experiments based on the feedback that you get, improve your MRV over time towards your next crediting event, which at that moment is quarterly for us, so 4 per year, and around we go. So I think this is the cycle that we're happy to be in. This is just to say that this is a real thing. It's an exciting time to be doing this in the field and doing the whole process end to end. And with that, I'll say if you are in town next week, please do get in touch. I am organizing a site tour for folks, but it's pretty limited in terms of how many people we can bring. But please reach out and we'd be happy to talk anytime.
Awesome. Thank you so much, Will. It's great to have an example and make all of this a little bit more tangible. Sometimes it can feel quite theoretical still. I know I see we have one question in the chat specifically for you, I think, Will, about types of sensors that you're using. Maybe you could take that one.
Okay, yeah. So the most important sensors we have are pH and turbidity or backscatter. So the turbidity or the backscatter sensors are used to understand particles because we're intentionally adding particles. Those are the types of measurements that regulators require us to make because again they understand the major risks here too. So we have permitted regulated levels that we keep a close eye on. And those are the most important. But then, we measure chlorophyll, we measure oxygen. We can't, I wish we had a sensor for trace metals, but those don't exist. So we take water samples for those. We measure alkalinity, we measure the typical things as well.
Great, thanks. Eliani, go ahead.
Thank you. Hi, Will. My question is, when you said you're scaling up, is that in terms of the volume of water that you're getting through that process? You make it bigger? Is that the case?
No, that's a good question though. So the flow through that system is always the same. It's just the power station pumping water. The way we scale is a few different ways we scale. One is kind of the most obvious. We turn up the pumps and we dose more mineral. So, when we started the project, we were dosing about 5 times lower rates than we are now, like 3 years ago. So that's the most obvious thing. But you also scale your removal some other interesting ways. You can use a feedstock that has a lower carbon footprint, right? So you're subtracting less, so you're doing more carbon removal, um, using the same amount of dosed material. Um, and yeah, there are other ways to lower the costs, but really what it boils down to is the rate that you're adding the mineral to the ocean.
And so the impact would increase by multiplying these stations that you have geographically? Would that be the future, I guess,
Exactly.
solution?
So at the power generation station there in the harbor, they have well, four different cooling loops actually. So they're drawing water in from four locations, discharging at four locations. So conceivably, you could add this mineral at all four
At those,
pipes.
right?
Of course, you have to be mindful of what the ocean can handle in the local area. So there is a scale to that for sure. The goal here is to sort of scale the project up until we sort of start to see where that limit is, and then of course move to the next, you know, wastewater plant or power plant. These places are always on the coast typically, and available to do that.
Thank you so much.
Any other questions from folks?
Put that slide back up. I will mention in the same breath that Sarah's mention of governance was an important one. And I would urge folks to look at the progress that's been made in Canada in terms of setting up these governance structures. So, for example, just last week, the Environment Climate Change Canada, um, one of the folks in that group spoke to the Senate in Canada and made it very clear to those senators that this type of ocean alkalinity enhancement that it's done at the coast, which is what this is, has and how it interacts with all these different governance structures, how it interacts with London Convention, how it interacts with Fisheries Act, and these types of things. So there is quite a bit of clarity there already, and for approaches like this. But that's not to say that we shouldn't develop um, things that are for this process. I think that would certainly be helpful. But there is already a fair bit of regulatory clarity in place, which is good. I
Yeah,
also,
Elioni.
oh, sorry,
And
go
yeah,
ahead.
thanks for that, Will. That was great.
Sarah, this one's for you. You mentioned the registry as the place where sort of the evaluation take place to confirm the bonds. Is that a global, and can you explain a little more about it? Is that like a global entity that works for any project, mCDR project? Is that country based? I'm
Yeah,
learning, so I'm just curious.
no, it's a good question. It's sort of complicated, but I guess just from a very sort of broad view, it's difficult. So when you're looking at like the carbon market, you can think about I think one thing that like we're sort of all aware of are like terrestrial like tree planting, right? And how that utilizes a carbon market. And so it's like if we plant X amount of trees and we can measure the amount of carbon that they uptake, and then you can sell those carbon offtakes, right? And we're trying to sort of develop a similar system for mCDR. But I think one of the big challenges is that each of these, so there's a bunch of approaches, right? It's not as simple as like planting a tree. So each of those broad approaches is going to have its own set of like protocols and standards. And then, as we saw, like as Will is mentioning, even within like one approach, like ocean alkalinity enhancement, like Planetary is using this one technique, other organ like Vesta is using a very different technique. And so then you even get like further complicated into like how would you write a protocol or a set of standards specific for that approach, right? That's appropriate. And so right now we're seeing some of these protocols being developed. And I think typically, well, Will, please correct me if I'm wrong here, but what we have seen are sort of protocols that are written with like one very specific approach in mind. Um, and which I think is good and necessary, but it also means that there's sort of a slowness to this, right? Because like can only really move so fast and you have to have this certain level of specificity. So I think it's like it's necessary, but it is also one of these not an obstacle, but it I think it adds to sort of the slowness of this field. Um and those projects to your question about like national versus international, I don't know that I have a great answer on that. I feel like most of the groups that I'm aware of are going to be North American based who have these standards and are participating right now. But Will, Eric, Ruth, if you guys have other insights there, please do jump in.
Yeah, I mean this protocol that we operate under, and I'll put a link in the chat. I'm not aware of anywhere outside of North America it's being utilized, but it is globally acceptable and can be used anywhere. I agree with Sarah that it's a challenge on one hand to have to be so specific in these protocols, but I don't really see another option in terms of I've heard a lot of people say that we need an overall MRV framework for mCDR, and I don't think that's possible because there's very little overlap across these approaches. So you kind of have to be specific. And in fact, the feedback about this protocol is that it needs to be more specific from our first crediting exercise. So, scientists they want to go down the rabbit hole, and that's what these protocols are intended to do, I think.
I love that. There is this balance. So I come from policy, and there is this balance of scientists wanting to be able to answer every question, every proof point that anybody could fathom, how much evidence can scientists find? And there's also this challenge of, the ocean, the climate really needs us. And if we're going to do something, how can we figure out if it is safe and doing what we want it to be doing, which is durably removing carbon, durable for like hundreds of years. So how much evidence do we need? So one thing I do want to be clear about, and again, I'm coming from the policy realm. Markets are still this like really strange place because I want regulations that, do things. That's what I understand much better. This is different. When we say MRV and we say monitoring, reporting, and verification, I just want to make sure that everybody understands that is for assessing whether the technology is doing the thing of removing the carbon and doing it at the levels that like Will and his associates would say that they're doing. Like, are they actually bringing down the carbon from the system and can they store it? The question of is it environmentally safe and doing an environmental impact assessment to figure that out and like what is doing to the environment beyond pulling carbon out, that is typically a different question. So that is something that, so on OAE, Carbon to Sea has currently public comments on a protocol for environmental assessment monitoring just for OAE. And then we at Ocean Visions, we are sponsoring a project right now for an environmental impact assessment framework for mCDR in total. And we're seeing if we can actually create something that overall would be able to start a framework for assessing the environmental impacts. So that because they are so distinct, all these different technologies, if you're looking at something biotic versus abiotics or chemical versus phytoplankton, that kind of difference, it might not be something that you can look at the same way. So I just want to make sure that everybody understands this difference between monitoring and verification and reporting, MRV, monitoring, reporting, and verification for carbon. And that could be for regulation, a public good, or markets, and the environmental impact, which is a lot of the first question that communities will have of what is this doing in my waters?
Thanks, Ruth. That's super helpful. We have a few more minutes. So while people go ahead and, if you have another question, raise your hand, come off mute, put it in the chat. I'm just going to launch another quick poll while you're thinking. Did you learn something new? It's okay if you say no, it won't hurt my feelings. And as people are thinking too, if you have a last question, do you want to just plug? There is a fisherman closed session tomorrow, I believe, happening, also in anticipation of the forum. If you are a fisher and would like to join that, perhaps reach out to Eric. I don't know if you're the right person for that.
Eliani, do you have the link for registration that you can pop in the chat real quick?
I'm looking for it right now.
Yeah.
Just
We'll reach out to me or we'll pop it in the link.
Great. Perfect. And then one last question. What are you most looking forward to at the forum next week?
If you didn't answer the food and drink, then you should reconsider your answer.
All right. Well, I'll leave this active as people fill it out, but just want to say thank you again so much for your time and attention. This was wonderful. Thank you again to Eric and Eliani for helping organize this, and Kalina as well. Thank you to Ruth. Thank you to Will. And happy forum next week.
Yeah, thanks, Sarah, to you and Ruth for leaning in and offering to do this because it's a big lift for everyone on a very busy week to attend and to put this together. And you all have so much expertise. It's nice to have you participate. So thank you for thinking about it and stepping up to coordinate it and do it. Really appreciate it.
It's our pleasure.
Thanks for the invitation. Thanks, folks.
Thank you.